Hello again. Welcome back. If you're watching these over the course of a week, yes, I've worn the same shirt for days and days and days. Okay, in this video, I'm going to go through the derivation of the third kinematic equation. Sometimes it's called the v-squared equation. So it has a little bit different characteristic functionally. This is an equation which involves velocity and position and acceleration information, but not time. But it's really not it's not different information than the other two that we've seen in the previous videos. It's just a repackaging, a combination. For some problems where they don't give you information about time and they don't ask that you find time, maybe this is just will be a faster route to the answer. Anything you can get with this equation, you can get with the other ones and vice versa. There's not one that's better than the other. It's just a repackaging. So to do this, I guess I asked you to kind of bear with me. This video is going to be a little bit more, I don't know, jumbled. We're going to go through some algebra, and as before, it's all going to be symbolic so that the result will work for any scenario. So we don't have to worry about special cases and like what happens if you double the acceleration and you have to do everything again. No, we're going to have equations which work for any scenario, and we just use them and plug in the appropriate values. So let's start by reminding ourselves what kinematic equations 1 and 2 were. And then we're going to talk about a plan to eliminate time from them, and then we'll see what we get. All right. So kinematic equation 1 said that the velocity as a function of time equals the initial velocity plus the acceleration times the amount of time. That's fast. And kinematic equation number 2 said that the position as a function of time is equal to the initial position plus the initial velocity times time plus 1/2 the acceleration times the time squared. Those are the two equations that we derived in the last two videos. And they're good enough. To be honest, you can solve any problem with those, any uniform acceleration problem with just those, but it might be a little bit longer. So we can kind of do some of the algebra beforehand and derive kinematic equation 3, and that might make some problems faster. That's good. All right. So the goal for kinematic equation 3 is to get an equation to describe the motion, which has to be compatible with these two, where time does not appear. Okay. So we've got two equations, both involving time, and we want to get a single new equation without time. So, well, okay, it's just like in algebra class. When you want to eliminate a variable from a set of equations, you first solve for it and substitute in one equation, and then substitute it into the other equation, and then it's eliminated. And we have two ways to do this. We can either start with kinematic equation 1, rewrite it to solve for time, get it into the form t equals blah, 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 and plug it into kinematic equation 2, and clean it up, and we get our answer. Or we can start with kinematic equation 2, rewrite it using the quadratic equation, because it's a quadratic equation, to say t equals blah, 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 and plug it into kinematic equation 1. So either you start with 1 and plug it into 2, or you start with 2 and plug it back into 1. But you're going to have to do some combination of those. Now, it doesn't matter. Well, all roads lead to Rome. However, you have a choice. One of those two routes is a cookie, and the other is a kick in the head. And when life gives you a choice between a cookie and a kick in the head, and it doesn't matter what you choose the cookie. Okay? So I would look at this and say it is far easier to solve for time in the linear equation and then substitute it into the quadratic equation than it is to solve the quadratic equation and substitute it into the linear equation. Because then you don't have to deal with the quadratic equation and square roots and all this stuff that you just don't want to deal with. So let's do that. Let's start with equation number 1, and then plug the expression for time into kinematic equation 2, and then we'll rearrange it and see what we get. I claim that's the cookie. I didn't say it was a good cookie, so maybe it's like, oatmeal raisin or something that, it's kind of in there in the bottom of the tub that nobody really wants to touch. But okay, it's still better than a kick in the head. So that's what we're going to do. All right, so we're going to take the cookie. It's oatmeal raisin. Looks like chocolate chip, but it tricks you. It's oatmeal raisin. Maybe it doesn't taste that great, but it's the best we've got. So what the idea is, we're going to start with kinematic equation number 1, and we're going to solve that to say t equals stuff. And then once we have that, we're going to substitute into kinematic equation number 2. So, and then we're going to rewrite that, and tell you what, we're going to rewrite it so that we get v squared equals stuff. That's going to be the goal. I only know that because I know where we're headed, but that's the plan. Kinematic equation 1, get it so t equals stuff. We'll have to figure out what that is, and then substitute into the second equation and get a result. Okay? Before I do that, I'm going to do just a tiny bit of kind of processing. Oh dear, I have a typo. Son of a gun. I said initial position, but I wrote initial velocity. Hopefully you caught that. So I'll do that in green. This should have been x initial. I hope that didn't throw you off. I'll try to highlight this when we meet live. Okay, should have been initial position that was sitting there, not initial velocity. The initial velocity is in the second term. The details really, really matter. Okay, what I'm going to do is rewrite this one just slightly and go back to one of the other ways I wrote this to say delta x is v initial t plus 1/2 a t squared. Just turns out that's a little bit more handy for this activity, for this derivation. It's equivalent because x minus x initial is delta x. Apologize for the mistake. Thinking about too many things at once. Okay, so we've got a roadmap. Let's follow it. I start with kinematic equation number 1, and I rearrange it for time. So that says v equals v initial plus a t. If I want to solve for t, I can subtract the initial velocity over to the other side and then divide by a. So I could say v minus v initial equals at, divide both sides by a, and I get, and then flip it, say that t equals v minus v initial divided by a. The whole thing divided by a. All right, I've just rearranged that to solve for t. I look at my path. Okay, I've gone through the first step. Now I need to substitute that into kinematic equation 2, and I'm going to plug it into this form of kinematic equation 2. Okay, so I'm going to take this and plug it into this form for kinematic equation 2. I'm going to get delta x equals v initial times time, but everywhere I have a time, I'm going to replace it with this. Ooh. That looks ugly. I promise, though, it cleans up a bit. But it is a little ugly. I will grant you that. Plus 1/2 a times time squared. Holy crap. Let's square that. So that's v minus v initial squared divided by a squared. I thought this was supposed to get better. This is looking worse. It will get better. And we have to expand things out. So we're going to distribute the initial velocity into the parenthesis, break this apart. We're going to clean up, we're going to cancel this acceleration with one of these two and expand. What do you call that? Foiling? Foil. Yeah, that's what we're going to do. We're just going to expand it out. I don't know what these things are called anymore. You do math. You just do math and do it right. Okay, so let's do that. So this is going to be V initial times V divided by A minus V initial squared divided by A. And I know what you're thinking. You're saying, Sean, you promised it's going to get better. And it will, a little bit, within reason. 1/2 over 2. This acceleration cancels with one of these, so I get 1 over A. And then I have to expand this part. So that becomes V squared minus 2V initial V from the cross term plus V initial squared. That's still not pretty. Now, I can combine these into one fraction, 1 divided by 2A, and I can distribute that across to each one of these terms. So I'm going to do that. I'm going to have the delta x equals V initial V over A minus V initial squared over A plus V squared over 2A. Now look here, I have minus 2 V initial V over 2A. The 2's cancel. So I get minus V initial V over A. I just have to distribute and be really careful. Plus V initial squared over 2A. I'm almost there. There's a cancellation. That's kind of part of the cookie. I'd say it was a really good cookie, but that's what we get. So this term cancels against this term. And furthermore, if you think about it, this is V0 squared over A with a negative sign plus V0 squared over A, and there's a half. So in fact, these two pair up to give negative V initial squared over 2A. This is it's like there's a minus 1 here, and there's a plus half there. So minus 1 plus a half is negative half. That's how you can think of it. So now we're basically there. I'm just gonna rearrange these, combine these terms that I can, and I have that delta x equals, let's write the positive term first, V squared over 2A minus V initial squared over 2A, right? That's the term. When I combine these, that's what I get with a minus sign. And remember I said the goal was to write it so it says V squared equals blah, blah, blah. Well, let's do that. So we want to solve for V squared. So I want to move this across the equal sign, and then I'll have to multiply by 2A, and that will give me my final expression. So I'm going to get V squared over 2A equals delta x plus V initial squared over 2A. Just moving this across the equal sign and just rewrote the whole thing. And now I'm going to multiply both sides by 2A. So I pick up a prefactor here and it cancels that denominator. And I get V squared equals V initial squared plus 2A delta x. Dun, dun, dun. That is our third kinematic equation. Kinematic equation number 3. This equation is going to be useful when we don't know the time and we aren't required to find the time, or maybe sometimes it's not even possible, depending on the details of the problem. or very hard to do so. So this is there. This problem, this equation is can be useful. It doesn't. I find that it doesn't always get used quite as much as the other two. There's one other caveat. It doesn't actually give you the velocity. It gives you the velocity squared. So you have to be careful with minus signs. If something's going right or left, this term doesn't know the difference. And so you have to be careful and think about it physically. Just picture it to know, should you choose plus or minus. We're going to be doing lots of examples, and you'll see all this come out. So, all right, thanks for watching. Next up, we're going to start using these equations to solve problem after problem after problem after problem. And hopefully it'll all start to come together in a sensible fashion. So we've now seen kinematic equations 1, 2, and 3.